Welcome to this Eclipse tutorial series. My name is Michael Traeger, and I created these videos while finishing my master's degree at Duke University. This tutorial series was funded by the Medical Physics graduate program at Duke University. These tutorials will be focused on providing an introduction for students in the Duke Medical Physics graduate program with respect to a project they will complete during their radiation therapy class, but can be extended as a useful tool for any beginner Eclipse users. As a disclaimer, these videos are not meant for use as guides for clinical applications, including treatment planning on real patients, rather as a good starting point to familiarize new Eclipse users. I'm not affiliated with Varian Medical Systems or with the ARIA software at this time, and am by no means an expert user. In this video series, I will cover the basics of the Eclipse interface, getting started with the treatment plan, contouring strategies, basic 3D planning, IMRT planning, and how to analyze plans. I'll be working with Eclipse version 13.6 and ARIA version 13.6. Alright, let's get started. This is the first video of the Eclipse tutorial series, Eclipse Overview. In this video, I will discuss how to navigate Eclipse, open an existing patient plan, and discuss the interface of the External Beam Planning functionality. This is the home screen of ARIA. ARIA is a comprehensive information and image management system. ARIA lets you oversee all aspects of oncology care. All radiation, medical, and surgical oncology information are kept here in a complete oncology-specific electronic medical records database that allows you to manage the patient's entire treatment, from initial diagnosis through post-treatment follow-up. We'll be focused on a few specific functions within the treatment planning functionality of ARIA: external beam planning, contouring, and plan evaluation. From the main menu, you can access your favorites as well as any other functionality of ARIA through the Quick Links drop-down, seen here. This is a drop-down menu that allows users to easily switch between different categories. For now, we will open an existing patient. To open an existing patient, we will use the text box at the top of the screen. Here, we can enter the patient's first name, last name, or patient ID, as well as pull up the advanced search screen here. For this tutorial video, we will open this first patient, which is anonymized. Once the patient is open, we can see all of their information and treatment information. For now, let's open the external beam planning functionality. Once we select our patient and go into external beam planning, we will be prompted to open an existing course, which is a collection of plans, and then the plan or plans we would like that are associated with this course. For now, we will open a plan I have previously completed. When a plan is opened, all associated image sets, structure sets, and plan information are loaded. We can also have multiple courses loaded at a time in order to easily switch between various plans. To choose a specific plan to work on, we can drag and drop the plan into the viewing window. I'll discuss a few of the things we see now. We have 4 views here: transverse, coronal, sagittal, and a 3D depiction of contours, dose, and treatment fields. There's a little human figure at the bottom left corner of each view that can help to orient you to the current geometry of each view. To access the dose volume histograms for the current plan, we right-click on the 3D view, then select Show Dose Volume Histogram View. To get back, we can do the same thing. We can scroll with the mouse to go through each slide in each current view. We can also use these slider bars, which go a little bit faster. If we want to enlarge any of the views, we can simply double-click on its header, and then do the same thing to go back. A nice little trick to zoom into a view is to hold the control button on your keyboard and then scroll with the mouse. On the left side, we have a window that shows the current patient, current courses open, and current plans open. We can easily switch between different plans and courses. Underneath, we have a list of all the plan objects. So here we have all the images loaded, we have registered images, we have all of the contours associated with the image, we have reference points, dose, and all of the fields. On the top of the screen, just under the file bar, we have a bunch of nice features. We have buttons for dose calculation, we have a ruler, we have point dose and dose profiles, windowing and leveling, and various other features that we'll get into later in other videos. A nice shortcut for switching between different features in ARIA is this workspace bar. We can open this through the window drop-down and then click on workspace bar. Here we can switch between selection, contouring, image registration, external beam planning, plan evaluation, and other functions that you have in your current version of ARIA. Lastly, we have these tabs underneath our viewing windows. There's a lot of functionality down here that we will be using, so I'll describe each tab in detail. First, we have the Fields tab. Here we can see all of the treatment fields that have been added to the plan. We have information about the field name, the field technique, whether it's static or it's an arc. We have the machine that the field was created on, the energy of the beam. We have the MLC motion, whether it's dynamic or static. We have fixed weightings, which are pretty useful for getting hard to reach dose distributions. We have a scale, which defines how the linear accelerated geometry is defined. Various scales can be set, which for example may define the gantry, couch, or collimator angles differently. So let's say 0 to 360 or negative 180 to 180. We have information about a wedge if it's used in any of the fields. We also have valuable information about the geometry of the fields. So we have the gantry rotation, collimator rotation, and couch rotation. We also have dimensions of the field as determined by the jaws, which are the primary collimators. We can individually set each side of the jaws in both the x and y directions specified by x1, x2, and y1, y2, or we can use a uniform jaw dimension, and Eclipse will use uniform dimensions for both sides of the jaws. So to do this, we use field x or field y. We also have information about the isocenter. These three values, x, y, and z, are the translational distances from the user origin, which for standard practice here is also known as the CT0. These shifts are essential when the radiation therapist is shifting a patient from the CT0 to the isocenter on their first day of treatment. These shifts are specified with respect to where you need to move the user origin in order to get it to the designated isocenter in your plan. We also have the calculated SSD and the total MUs for each beam. Next up, we have the Dose Prescription tab. This tab holds all the information about the dose prescription. We have the prescription dose per fraction, number of fractions, and total dose. Next, we have the target volume. This volume is the target that we want to receive the prescription dose. This will also be the target volume used for certain dose normalizations. The primary reference point is a point that records dose after each fraction of treatment and saves a running total of dose delivered. This point can correspond to a physical point within the patient for which we can calculate the dose, or it can be locationless, so that the dose per fraction associated with this point is simply the prescription dose. This is important during treatments because it is a safety mechanism to avoid over or underdosing a patient. We know the total dose delivered to this point at any time throughout the patient's treatment, and whether or not that value matches the expected dose at that stage of treatment determines if the patient has missed a treatment or has been treated extra. Next, we have the prescribed percentage. This indicates which isodose line of the treatment plan corresponds to the prescription dose. For instance, if a physician looks at a plan and decides that the best coverage is achieved by the 95% isodose line, they can enter 95% here. No changes occur to the relative isodose lines, however the absolute dose for which they are associated will be scaled so that the 95% isodose line is associated with the prescription dose. The next important value is the plan normalization mode. This allows the user to scale the monitored units in such a way to achieve a desired coverage or normalization layer. Here, we can choose various methods of normalization. The most common method of normalization is this fourth option. Here we can specify what percentage of the prescription dose we want to cover some percentage of the target volume. A common combination here is to say that we want 100% of the prescription dose to cover 95% of the target volume. We must be careful when normalizing, however, because the treatment planning system will force our plan to meet these normalization criteria, and may therefore largely over or underdose other regions. We can also normalize such that 100% of the prescription dose occurs at the target's maximum, mean, or minimum dose, 100% at the body maximum, primary reference point, or another reference point. Another useful normalization method is to simply use a plan normalization value. The plan normalization value is relative to the default normalization that the planning system initially provides. In rare instances, this method might be useful to manually tweak the plan normalization by a percent or two. Lastly, we can also choose normalization and leave the dose distribution as originally calculated by the treatment planning system. Next tab is the Plan Objectives tab. Here we can view plan objectives that would be dictated by a specific protocol. I do not currently have one loaded, but we would be able to see if various dosimetric criteria are met, including a percentage of the prescription dose that covers a certain volume of the target. The next tab is the Optimization Objectives. The Optimization Objective tab is similar to the Plan Objectives tab. However, this tab will list optimization objectives from your inverse optimization and whether or not the specific criteria chosen is met. I will get into inverse optimization in a later video. This is nice for a quick indication if you exceed your OAR constraints when you are normalizing. However, it is most effective to get a broader picture of the dose distribution from the isodose lines or DVH. That brings us to our next tab, the Dose Statistics tab. This tab is useful for finding out information about the dose delivered to each structure and to create DVHs. As you remember from earlier in the video, we can pull up a DVH by right-clicking on the 3D viewing window and selecting Show Dose Volume Histogram View. We can then maximize the screen by double-clicking on the header. Once the DVH screen is up, we can choose from a list of all structures in the plan and create DVHs. So as you can see, as I select the structures down here, it populates our DVH. We can also switch between absolute and relative dose and absolute and relative volume. I'll discuss how to use the DVHs in more detail in a later video on analysis. Also in this tab, we have various statistics that are automatically generated by checking a box next to the structure. So as you can see, as I select this box, it populates all of the statistics here. We have the volume, the dose coverage, the minimum dose, maximum dose, and mean dose, as well as other built-in functions that can be customized by right-clicking on the top menu and selecting View Columns. So we can select other functions here, and then they pop up down here. We can also add our own expressions. To do this, we click on Add Expression, and this allows us to use Boolean logic and our structures to create new structure expressions for the sole purpose of analysis. This is useful if we have a target that is within a critical structure. We can subtract out the target volume and be left with dosimetry for only the healthy region of that structure. The next tab is the Calculation Models tab. Here we can view all of the current calculation models used for the dose volume, compensator, IMRT and VMAT optimization, and more. You can also select older models if they are still present in the treatment planning system. This is useful for research because you can use functionality that might have been discontinued in newer versions. The last tab is the Plan Sum tab. This is useful when you're doing a plan sum. Plan sum is just as it sounds, the summation of the dose, fields, etc. from two plans. This is useful for analyzing total dose delivered when creating two plans for a single patient, and it will only pop up if you've created a plan sum. For example, if we have a breast patient who needs supraclavicular nodes treated, we can combine the plan that irradiates the breast as well as the nodes to get a composite dose distribution, or we can use this for patients with recurrent disease in order to assess dose to critical organs that have previously been treated. Thank you for viewing this first video in the Eclipse tutorial series. I hope this video was useful and that you now understand the basics of the Eclipse user interface. My next video will help you get started with your own treatment plan. I'll see you next time.